So looking now at the second problem on the third self-assessment sheet, we're going to look at a common scenario that you have in bioprocesses where even in a continuous reactor where you've stuff flowing into the reactor and you've stuff flowing out of the reactor. All those kind of situations involve what's called a startup phase, where you start from time zero, and then, if you like, the system kind of gets up to speed, so to speak, and eventually gets to what we call a steady state, where the inlet conditions are constant and the exit conditions are constant. But that takes a certain amount of time, and it's often a complex part of a process. So what we want to do is model this process. So we've got an enzyme catalyzed reaction going on. So our substrate here is what's being consumed. And so we have substrate flowing in to the reactor, we've substrate flowing out of the reactor, and then we've substrate being consumed in the reactor. So it's a relatively complex problem, and this bit here is called the Michaelis-Menten kinetic term, famous equation in biochemistry. So we'll code this equation, and if I go into Berkeley Madonna, I've set it up as well. I've put in all the parameter values again, so I'm not foostering around going back and forth. So we'll do the differential equation first, and that's d dt of s is equal to q over v. By the way, q over v, if you look at the units of that, it has units of 1 over time. And biologists tend to refer to q over v as the dilution rate. So it's almost the rate at which fluid is going through a system relative to the volume of the system. So it's something that you'll meet in fourth year when we study bioreactors in more detail. That ratio is usually given the letter D, and it's a very important parameter in terms of understanding what biotechnologists called chemostats, which are continuous bioreactors. Anyway, so we have Q of V times the substrate coming in minus the substrate going out minus the substrate disappearing due to reaction, which is V max by S over Ks plus F. And our initial condition is equals, so initial S is S0. Let me just double check that S0 is equal to 0 is right. Okay, so that's fine. So that's our model. So we've just tried to adopt a systematic approach. In other words, we're trying to solve every problem in exactly the same way. By the way, the order here doesn't have to be the way I'm doing it. You could have the differential equation last, and that's one of the things about Berkeley Madonna that's particularly user-friendly in the sense that you don't actually have to worry about the order in which you put in your equations, and that's very different from most programming languages, where very often the order is really important, and if you get things in the wrong order, the computer just can't do the calculation. Anyway, so we'll get our windows sorted out just to follow best practice, and we'll put our parameter window in there. Oh, didn't know it would do that, so I had a little error there. Anyway, so I didn't know it. When you move the parameter window, it checks your code. So there we go. So it has all those values in there already because I've given them here. So I'm going to leave the stop time as 10 for the moment because I don't really know what this model is going to look like when I run it. So I'll run the model now. Stop time of 10 seems to be okay. I think I haven't really specified any units for these parameters here, which is a bit naughty of me, because one thing about doing engineering is that you really have to be strict about making sure all your units are correct. But just to make life easy for ourselves, we're not specifying what these units are. Anyway, so what we have here is that the concentration of the substrate starts at 0 and then increases up. And let's just increase the stop time a bit there to 20. And we're going to run it again, and we can see that it reaches this value here. And remember, the feed comes in at a concentration of 10, but it starts leaving at a concentration below 9 because obviously some of it's being consumed, so it's coming in at a concentration of 10. There's a reaction going on that's catalyzed by the enzymes, which is reducing that concentration. So it's now coming out, and what we call its steady state value is 8 point something. Now, if I were to increase the Vmax, so let's make Vmax 5, I think that should probably bring this S value down. So I'll just put in an overlay so we can compare, or I might just make it take longer. No, it should bring down the concentration at steady state. Yes, so we have the rate of reaction is greater now with a higher Vmax. So while the substrate comes in with a concentration of 10, because it's being consumed, it's coming out with a concentration of just less than 5. And that's to be expected, because if you look at the equation here, you've got stuff flowing in and stuff flowing out, but you have this additional consumption term. So logically, there has to be less coming out than is going in. So that's what you call your startup phase, and until you get to steady state. So it's a very common problem in bioprocessing, and very often the startup phase can be quite complicated mathematically, and that's why something like a simulator that we're using here makes everything so easy, really.